我说还差几秒，就他那个已经快了5分钟。
越来越快。
Okay, today we're going to start the lecture with 2 short subjects. The first one will be the effect of sampling rate. It's how sampling rate affect us. The next one, I will talk about a conjecture and a theory on EMD. The effect of sampling rate should be a pretty important problem for every experimentalist. When you take data, how fast you should digitize it. Of course, the more the better, but then it's limited by resources. Should you take more data per unit time, or take a longer data to cover long period of time with given storage, and also given the data analysis resources? If you take too much data, too many data points, then it will be hard for you to analyze it. So another question is that if you want to observe something, and what's the minimum number of points you would like to have in order to resolve it? And that is known as the Nyquist frequency. This is the the highest frequency that you can resolve. In the past, we only say the Nyquist frequency for Fourier, which is 2 points per cycle. If you want to observe 100 hertz phenomenon, at least you should take 200 hertz data. In other words, each second you should take 200 points. Now, what should be the Nyquist rate for EMD or HHT? Only recently, Rayling started to study this, and his study is very theoretical, and he reached this conclusion. He said that if we have a simple sine wave, simple cosine wave, given like that, and you start to sample it, you're sampling. It's all the time that we'll talk about as if sampling is not a problem, because we always talk about continuous function. But in fact, the function that we deal with in the form of data, it's never continuous. We get 1 point, and then another point, another point. So these points, it's very, it's discrete. So then if you undersample discrete data, we'll look, instead of the continuous 2 pi t, it actually looks like this. It depends upon how frequent you sampling it. And then he finally deduced that if the first IMF is dn, then the true value, compare your dn, is given by this. And this value is less than pi cube over 8fs squared, where fs squared is the sampling rate. Okay? This is given by this. And so it depends upon how frequent you take the sample. That determines how much the error you have. So this is the error, how much the error you have. And if you're interested in the full proof of this, you should go to Advanced in Adaptive Data Analysis, Volume 1, 43 to 59. The whole proof, it's pretty theoretical, but by and large, you can see that. See, if, for example, you put k equal to 1, what happened is 2 plus 1 is 3. 3 squared is 9. 9 times 8 70, 72. And pi cube, it's about 30. So if you take 1, this is about 70 to 30, it's about 50%. If you take 2, it's much better. So this is the effect. If we take k equal to 1, it's about 50. Take k2, it's about 15%. So this is what they find. But this is only with regard to the IMF with respect to the first true data, the signal itself. But we are interested in more than signal. We are interested in addition to signal, we're interested in frequency value. Yeah. Once you get the data, what kind of instantaneous frequency can you get? Because we want a time frequency analysis, not just get a component. Yeah. The component may look good, but the frequency doesn't look good, and our time frequency analysis still will not find the right answer. I cannot find anybody prove this theory or establish any criteria, so we decided to do it empirically. The empirical study is like this. So suppose we have a sine wave, which is continuous, and we have 1,000 points, which make look practically continuous. But this is never the data we got. The data we got is usually like this. If of this period of 100, we get, say, 19 points. That means on each wave we get about five data points. So even 5 data points, you see what we have is that we miss the peak. Yeah, and when you have data which looks like this, what your impression is that, of course, the maximum is this, and this maximum is here. You will never think the maximum is here, because there's no way for you to tell from the data, so where is the maximum? Yeah, where is the true maximum? We only got whatever we got. And here I use 19, just make sure that it's not an even fraction of the data points. If we use even fraction, you can design so that they always get a maximum. Yeah, but in this way, we miss a lot of maximums. Yeah, and if you get data and you're not sure of the data, what can you do? What can we do? And I suggest a upsampling. So we have used downsample before. So if we get too many data, we just downsample it to roughly something like a 5 or 6 point a wave. Here, we get the data. We don't know what's going on. So what if you upsample it? The reason that we upsample it is that our final answer is always a spline. So if we use upsample, use a spline, we'll never compromise the answer we got, right? Because whatever you got is already spline. So if I use a spline to upsample it, it should have no impact on our answer. So if I use spline on the previous data, on this discrete data, I use cubic spline. What I got? I get this. I almost recover the data. So after you use the spline, then you resample this, then you'll get the full. This spline means you put it in 5 more points in between. So once you put 5 more points in between, you got it. You got almost the original copy. Okay? Now, let's see. For 100 points, I only take 23. That means each wave roughly has 4 points, a little bit more than 4 points. Now, we miss the peak even worse. A lot of the points we don't we missed the points already, missed the extreme already. Now in this case, if we take this data and I say, all right, I will upsample, upsample rather than downsample, upsample. What I got back almost the original. Yeah. So 4 points a wave, it's no problem. We can almost fully recover the information. Now, with 4 points, how about 3 points? 3 points. Look at this. We have the data already missed a lot of these. Almost we hit a few, but most of the peak we missed. So if the data you got is only 3 times of the frequency that you want, beware. We are very poorly the true phenomenon is very poorly represented. Yeah, and in this case, if we again use spline, we get back to this, which is not too bad. It is okay. We miss this, miss there. Now, if we go to Nyquist is 2 points a wave. Look at this, what do we got? This is roughly the situation that we have for 2 points a wave. We roughly get the frequency right. That is what the Fourier wants. Okay, Fourier get roughly the frequency right. But we want to get not only frequency, we want to get the energy so that we can get time frequency analysis. So our requirement is much more stringent than the Fourier analysis. So if each wave we only get the 2 points, our answer is very, very bad. And in this case, even if you want to do upsampling, the frequency is a little bit off, but roughly, if you use Fourier, you still get that same peak. In other words, the frequency still comes back. So this is the effect of sampling rate. Now, in addition to this, so for this data, if I do a EMD, what I get the first component almost look like that. The second and third components, there's not much information. This is 1, this is 4%. So it's not, even if you add it back, it's not much you can recover from that. But this is from the upsampled data. But if you use the original data, this is the IMF. Without the upsampling, this is the first IMF because the data is discrete. So the original data, if you use original data, you will get this as first IMF. Again, there's no more information that you can add. This is only 2%. Yeah. So it's not much you can do if you only have 2 points a wave. Now, what if we have 3 point a wave? Upsample, you get this. And then the rest of that, 5%. So you don't care about that if you have 3 points and upsampled. You can get back pretty good. And what if you do not do this upsample? If you do not do the upsampling, you get the first component, you get the frequency correct. This is what the Fourier is after. You get the frequency correct, right? But what's the error? Error is 20%. Compared to the error of 5%, this is dramatically different. So this is what your error is. And this error has a structure almost. Yeah. This is for 3 points. Now, if you get 4 points, the upsampled result, EMD, it's very respectable. Yeah. And the error, this is 10 to the minus 3, 1 part in 1,000. This is 1%. So if you have 4 points, and you upsample, you are very good. And even if you do, yeah, this is 3 points, 4 points. Oops, 4 points. I forgot to do the original data. I don't know why. Anyway, this is 4 points upsample, and if you get the if you have a 5 point, the error here is 1,000th. Yeah, and even the original without the upsampling, you still get about 5% correct. So the idea is that if you get 4 to 5 points a wave, your answer should be very good. Yeah. So this is the Nyquist frequency that we got. Now, how about when you calculate from the upsampled data to compute instantaneous frequency? Instantaneous frequency is still off. Don't let the waveform itself misguide you. The waveform looks good, but when you compute the instantaneous frequency compared to the original, the error is around 6%. So there is still error. That's why the instantaneous frequency is a something which I think is much more precise, much more accurate than Fourier. When you average this, sometimes you get a positive, sometimes negative. The average is perfect. The mean value is perfect. But the instantaneous value tells you what is wrong. The instantaneous value still tells you that even the waveform looks good, even if the mean value of the frequency looks good, the instantaneous frequency, even you have 5 points, there are still errors. Yeah, the error accumulates. Yeah, and if you have 23 points, the error is almost up to around 7 or 8%. So 4.5 points a wave. The waveform, the energy is no problem, and the frequency, even instantaneous frequency, looks respectable. Yeah. However, if we keep on going 3 points, then you see the error? The error now is almost 18-20%. So by the time 3 points, even though the waveform, we recovered the waveform very well, but the instantaneous frequency is spread all over the place too, almost 20%. Now, if you use 2 points, remember, the average value is still good. Okay, this is what the Fourier tells you. The average value is still good. But the instantaneous frequency, 100%, 50%. So instantaneous frequency is totally useless. We cannot trust the instantaneous frequency anymore. So for 2 points, Nyquist frequency, the Fourier Nyquist frequency, to us, give you this kind of result. Yeah. So in our study, we should really try to get the data as dense as possible. Now this exercise is just for a sine wave. Now what if we have a random signal like this? I don't know where I get this signal. I just grab a signal like this. This signal is very dense, of course. It will give you all kinds of little things. Then I sample it. What if I take data like this? This is the full data. This is undersampled data. Undersampled data given by this green. The green data and the original data looks almost the same. Then I spline it back to try to recover it. So the difference between the red and the green, it's not much. Yeah. But if you start to do, you look into that, we missed here a little bit. We missed here. This is the peak, but the peak is almost recovered. The peak is almost recovered. Only the high frequency. That is where we have problem. We only have 2 points a wave. So high frequency wave, we are encountering difficulties. Now, when you do EMD, what you have? The EMD for full data is the dotted line. It's very good. Undersample is the green line. And spline is the red line. So most of the place, the spline, here we missed it. This is high frequency, we missed it. Here, we improve a little bit from there to here, but we're still off. We're still missing the high frequency. So this is the area that we have only 2 points a wave, that we should be prepared that we're not going to recover anything meaningful. But sometimes the damage is not only limited to that. This is the first IMF you expanded out. The first, this is without upsampling. This is with upsampling. We get a little bit of the high frequency flavor, but not the truth. Now, the second IMF here, we have big problem because of the mix of that high frequency stuff. The high frequency actually spill over to here. Yeah. Now, this is the original. The second IMF after upsampling already captured this wave. And if we look at the third IMF looks like that without upsampling. And with upsampling, we get a very respectable results. Now, here I warn you is that, well, in that case, we have to be careful about the high frequency. True, but this is not the last example, last IMF. You can keep on going. This gets to 0.1, but you should look at the original data. The original data answer is 0.2. Yeah, this we got here is 0.1. So this in the intermediate state scale phenomena, we have already grossly compromised the answer. Yeah. So when your data is poor, the poor data can pollute your answer, not only locally, but also spread out to higher frequencies. And if you go to the to the IMF 3, what you have is that this is original, this is upsample, this is without upsample. Yeah. So the difference is all over the place. So in summary, based on theory and empirical study, sampling rate should be 4 times, not 4 times Nyquist, 4 times the sampling, 4 times the frequency that you want. So the Nyquist frequency should be 4 times the frequency you want to get. Okay. Spline upsample could improve EMD. If there's something which you doubt whether this is good or bad, then you should use upsample. We have done downsample, right? Have we discussed downsample? Give you ensemble downsample. I forgot. Anyway, if the sample is very dense, we can downsample. If the sample is very sparse, we should upsample. The goal is to hit the Nyquist 4 times of the frequency that you want to look. Yeah. If you get that, that's all right. And if we do this 4 times sample, also can almost guarantee that your Nyquist, your frequency, instantaneous frequency, is still respectable. So now here, I want to give the class a problem. This problem is homework as well as examination, because we don't have final examination. I would later type up the assignment and post it. But what I want you to do is to get any data you want. Maybe we should give them a data. Why don't we'll give you data. We use length of day data, okay? We'll cook up the data. And I want you to downsample it. After you downsample, try to use ensemble EMD to see whether you can recover it, with or without upsample. So I can take the data, downsample it, give you the data. Right? I give you the original data, give you the downsample data. And then after I downsample it, I will do EMD on the downsampled data. I'll do EMD on the upsampled data. I'll do EMD on the do ensemble EMD on the downsampled data, and ensemble EMD on the upsampled data. Compare this. So that's a exercise that you can get yourself familiar with the operation of EMD and ensemble EMD. Okay, so with that, this sampling rate question is done. I hope when you design in the future, when you design an experiment, you be sure that you have the data 4 times of the frequency you want to resolve. All right. Now, now we'll proceed to the next one. A conjecture and a theory. This, we come back to, again, wrap up the EMD. First, a conjecture. What should be the stoppage criteria? I have, in the class, I've said we should keep the shifting number, repetitive shifting number, as low as possible. Yeah, and how low is low? High shift number actually give you lots more details. Should we go for that? Yeah, but it turns out there's more detailed separation, but has less physical meaning. Yeah, we have to make sure. So, how low is low? How high is high? What is the optimum number? That is the question that we are trying to look for. Now, this is the example that I give in the original paper. Here, there are 2 frequencies. One frequency is 32 hertz, the other one is 34 hertz. 32 hertz sine plus 34 hertz sine give you a beat. Okay. Then we try to decompose this. When I submit the paper, one of the referees said, your method, it's no good. This is 32, 33. I use Fourier, I can separate the 2. Now you have to separate the 2 and show me that you can recover the 2 components. So at the beginning, I was not fully appreciate the EMD. I took up the the challenge. I did it many times of shifting. So now I'll show you what happened. Here we have many different lines. This is the original data, the black line. If I shifted 1,000 times, I do it once, do it twice, do it 3 times, and so on. What I get a red curve as the answer. The red curve all the high one get pushed down, all the low one get pushed up. That's what I say. EMD has the effect of even up the amplitude. So when you shift repeatedly, it gradually bring up the low amplitude and push down the high amplitude. So after 1,000 times, I get this red curve. And when I deduct the red curve with the blue, I get another red curve here. This red curve, when you look, it's almost like uniform amplitude. So essentially what I have is, I get the two sine wave out. Yeah. But if I say that if I only do 16 times, I do very little repetition, what I got is I get a black line. The black line is invisible. It's covered by the data. And the difference between the black line and the blue line is here. It's almost flat. So if you only do 16 times, you didn't do anything. The maximum is still maximum, minimum is still minimum. In between, 256 point is the green. The green, the difference is much larger, and 64 points is the magenta. Yeah. So by using different number of shifting, you will get either you don't perturbate this original signal at all, or you make the original signal almost look like a sine wave. When you make it almost look like sine wave, the difference then is this one. That means you actually separate the two frequencies apart. Now, the question is, do we want to separate the two frequencies apart? The answer is maybe not, because this amplitude modulation and the two separate frequencies, they are both mathematical representation. Sine A plus sine B equals 1/2 cosine A plus cosine A, 1/2 A plus B, or sine A minus B, or whatever. I forgot the trigonometry identity formula. But a sum of two sine waves can be written in the two forms. One is two sine wave, the other one is beat. What we provide is the beat frequency. Is the beat frequency reasonable? Yeah, it is probably reasonable. It's probably more reasonable than two sine waves. In other words, if I make one sound, one fixed frequency, but then I gradually modulate my amplitude, that is almost like two sine waves. Right? So your ear, can your ear hear the amplitude fluctuation with constant frequency, or you have to say that I heard two frequencies? So this is the question that we're facing. This two sine wave, the modulation, can actually, if you use EMD and use very, very high, you can actually separate it. But the separation is not meaningful, because this blue line is just as well an answer. So the effective of shifting is that you use 10 times, you use 1,000 times, you use 100,000 times. You get very different answers. Yeah. What's the difference? Is that if you use 10 times, yeah, you almost still get this amplitude modulated frequency. If you use 100,000 times, you get a constant frequency. So here is the dilemma. Should we go to separate the very detail or not separate detail? Yeah. So signal in black line can be decomposed into unit amplitude. That is, recover the constituent components of sine A and sine B. Yeah. If we want to do that, that is not what the EMD promised. That's what the Fourier promised. If you want to do Fourier, go ahead and use Fourier. If you want to use EMD, EMD gives you a totally different point of view. EMD gives you amplitude and frequency modulated signals. So that's the basic frequency. So decomposition with different shift number give you different answers, like what I was saying. Yeah. And which one is better? we can see using using different signals to illustrate that. And basically, what it is that if I give you a delta, depends upon how many times I shifting. 10 times I give you this. 2,500 times I give you more detail. Indeed, shifting more times give you more details. This is something like this. If I give you a random signal, yeah. If you shift only 8 times, fixed time 8 times. This is the first component, second component, third, fourth, and so on. This still maintains some randomness in that. But if you do it 4,000 times, what happens? So this becomes so regular. And every one becomes so regular and change so gradual. And why is this? Because now if we try to find the ratio of the mean period of neighboring IMFs, this is the mean period of this period to this period. Yeah. For example, this period to this period. In the original EMD, if we do it 8 times or 10 times, this is twice that, this is twice that, this is twice that, twice that. Okay? So if we summarize, this we have done millions of times of the data. And now we summarize the answer. The answer looks like this. This is the ratio of neighboring IMFs. Yeah. Neighboring IMFs 2. This bottom is log 2 number of shiftings. So this is 2, this is 3. 3, 2 to the 3rd power, this is about 8 times. 2 to the 4th power, this is about 16 times. Yeah. So when you do 16 times, when you do 8 times, the ratio is not exactly diatic. I've told you that the EMD is diatic. EMD is diatic is what? It's only at this point. That point is what? It's around 10. So around 10 times, you get the diatic. It happens to be diatic. If you get 8 times, the ratio is between 2 and 2.1. If you get 10 times, 16 times, it becomes more than 19. And after you did this many times, what you find is that the frequency gets closer and closer, the neighboring frequency. It's not diatic anymore. Diatic is here. And it gets decreased all the way down to around here. It's about 1.4. That is 2 to the 16 times. I forgot 2 to the 6. It was 2 to the 16 times. Anyway, this curve keeps going down. Yeah. And if you do 8 times, the separation power is this versus that. It's almost diatic. Almost diatic. And there are some common grounds. But if you do the 4,096 point, what you see is that this peak and peak are much closer. It's about 1.4 times. and the overlapping becomes more. Yeah. So the idea, the conjecture is this. If I keep on doing this, what will happen is that instead of very random, I get more and more smoothly changed. And if I do it more, and this will actually get more even and eventually becomes almost like that. Yeah. The conjecture is that if I keep on doing that, this is only 2 to the 16. If I do it infinite many times, what happens? If I do it infinite many times, will this gradually approach to 1? I think the answer is probably yes. Yeah. But then with the approach to 1, that's very serious. That means it will never be 1, but approaching 1. Approaching to 1 means it's almost like a Fourier analysis. It's a Fourier analysis, and as you go down, the number of components increases. Here I get 1, 2, 3, 4, 5, 6 components. Here I get 1, 2, 3, 4, 5, 6, 7 components. And if you do more, I get more components. How many components I will get for Fourier? Fourier get half of the data points. Yeah. This is here. We are far from half the components, far from half of the data point. But you look at this is almost constant amplitude. If I do the infinite many times, infinite many is a lot more than 4,000. It's a lot more than 1 million. Nobody have ever tried infinite many times. But the only time a colleague of mine tried is 1 million times. Yeah, 1 million times, it's every component is almost constant. But 1 million times is still not infinite. So the conjecture that we had is that if we do it infinite many times, will we get a sine wave? I don't know. This is conjecture. I don't know. I think it will approach the sine wave probably. So in other words, you just keep on pushing the amplitude even. Eventually, you may get a sine wave out. The only thing that we're not sure is that maybe the period, I don't know how much it will actually modify the period. But seeing from this kind of example, I think it influence not only amplitude but also frequency. So the frequency is always also get pushed too. So our conjecture is that EMD, if we apply it blindly to infinite many times, when we get a Fourier analysis out, we think maybe. That's our conjecture. No one can prove it. And we cannot prove it. Because we can only try, and whatever we try is far from infinite. Yeah. So, because of this curve, then we tell ourselves that if we want this to be dyadic, we should keep around here. And that is around 2 to the 3, 2 to the third, a little bit more than third. Actually, 3 is here. 3 is here. Yeah. So a little bit more than 3. So that's why in the ensemble EMD, we use 10 times shifting and stop at the 10 times shifting. So the conclusion here is the higher number of shifting, the smaller the amplitude modulation. Yeah. And the higher the number of shifting, the more IMF component we'll get. So to maintain the dyadic nature of that, we should be stay at 10. If you do the infinite many times, or it becomes Fourier, we don't know. But now, we made this statement. The higher the number of shifting, the smaller the amplitude modulation. Then come up a theory. The interesting thing in this class is that many of the things that we're teaching is actually created by the people around here. This theory is approved by Dr. Wang over there. Dr. Wang, in last year, he proved a very nice theory. And this nice theory settled some of the questions that we raised. The theory is that the definition, he picked out the definition of intrinsic mode function. The definition of intrinsic mode function is the same number of zero crossing extrema, no problem. The second one is a symmetric envelope defined by local maximum minimum. And Dr. Wang picked up this sentence. They said, well, this sentence has problem. Yeah. They say that if you enforce this symmetry, that means upper and lower, the sum has to be 0. Yeah? The upper and lower is the same function. And if you implement this EMD with cubic spline, then the only solution is straight line envelope. Right? That's the only logical conclusion is that the envelope has to be straight line. Otherwise, they cannot be symmetric. So if in pursuit of symmetry, you have to do it infinite many times. And do it infinite many times, you eventually comes to that. Then it becomes 0. We only think about that. And Dr. Wang actually proved that. Should I yield the podium to you to talk about your theory, or should I continue? How about I'll continue and you add whatever I missed, okay? Yeah, I will introduce the theory. I like the theory because it's very interesting. I've never thought of this way, and this is where the mathematician come out to keep us honest. Okay. Basically, there is a conflict between the definition of EMD and the method we implement. We implement the method with cubic spline. If you use cubic spline, you will never get a symmetric envelope. And only once that you get the symmetric envelope is the upper and lower envelope are all straight lines. Yeah. So we all live in the gray area. We don't want to push the truth to the bottom line. This is what he proved. This paper appears in Advancing Adaptive Data Analysis. It's volume 2, right? It's volume 2 or volume 3? Volume 3. All right. Let me type it down. Whoops. Volume 3. I don't know the page number. Anyway. All right. So how to prove that? Suppose these are the extremas. Maximums, minimums. Maximum you connect line. The maximum line is called the UT. The minimum line we call the LT. Yeah. What Dr. Wang proved is that if it's symmetry, then the UT and LT, even though we implement this piecewise cubic, but then Dr. Wang proved that piecewise cubic will be just one line, one uniform line going through. Yeah. Now, to prove that, Dr. Wang divided this by T1, T2, T3, T4. This is all the location of extrema. There's one additional assumption is that the in between the extrema, there at least should be 2 points. Yeah, and that is no problem because if it's 2 points, less than 2 points, we get almost near the Nyquist. It contains no information. So there are more than 2 points in between the extrema. Yeah. So the extrema is sparse relative to the data points. So then we compare in each of the time interval. Yeah. See, for example, from here to here, from here to here, from T2 to T3, we have upper and lower. All have to actually work for this section. And the theory is that we want to prove upper and lower is identical. And not only identical, they are the same line, same functions, no more function. No piecewise. Piecewise is the U1 over here. U1 is one function. U2 is another function. L1 is a third function. So by cubic spline, U1, U2, L0, they are all different functions because A, B, C are all piecewise determined. But if the function between T1, T3, T3 and T5, T2 and T4, if we consider the function in between T2 and T3, perhaps I should, if I consider the function between T2 and T3, these two functions are in the same region. These two, if the symmetry, it should be the same, right? If it's the same, then the upper plus lower should be 0 in T2 and T3. So if that's the case, then C1, Ci and Ai and Ci should be the same. Otherwise, it will not add up to 0. So, in other words, if this add up to 0, A has to equal to C. Otherwise, it will not be the same. At least we have 4 points in between. This has to be true. Then later, then after we consider this, then we consider this section. Then this L0 and LU2 has to be the same. So after this equal to that, this has to equal to that. So not only A equal to C, B has to equal to C, all over the place. So then, if A equal to C, B equal to C, if A equal to C, B equal to C, that implies the upper and lower are the same function, cubic function. Same cubic function with A with alpha, beta, gamma, delta. Okay, A equal to, these are all constants, all the same constant. So they are all cubic functions. That immediately you smell something wrong. If all the functions should be cubic function, we have even so. So the upper and lower, in fact, is unitary cubic function. Unitary cubic function already means that how many maxima you can have a cubic function. It's very few maxima you can have already. So that there, the problem is already there. But it's even worse because we use natural spline. What's natural spline means that the curvature is 0 at the end. So at each end, U double prime, V double prime, U double prime, L double prime, at the end has to be 0. And when you take double prime, means this take double prime, the only term left is A1 and A2. And if this has to be 0, then A1, A2 has to be 0. If A1, A2 equal to 0, at the end, that means everywhere A1, A2 equal to 0, because it's the same function. So then the function has to be A3 times A4, a linear line. So unless your data is monotonically increasing or monotonically decreasing, then so then your unitary function has to be u times a3 plus a4. And unless the envelopes are monotonic, that means your function can either go up or go down. If your function has any fluctuation at all, then this a3 has to be 0. Yeah. So the that proves the theory. So if we use cubic spline and we insist on upper and lower to be symmetry, then the envelope has to be constant. And this actually agree with the conjecture. The conjecture is if you keep on doing that, eventually you get constant amplitude. Yeah. Why can we continue that? Because the envelope has never reached symmetry. Yeah. If it reached symmetry, it stopped. It never reached symmetry. So whatever difference, it has to be a tiny little difference. It has to be there. To eliminate that tiny difference, you have to go one step more and one step more. And by the time you finish, you stop. You may not get to infinity, but when you stop, that has to be a constant. Yeah. So using cubic spline, eventually you get constant amplitude envelopes. That's what Dr. Wang told us. And if we learn from him, then we should know that we should not go to the limit. In other words, the shifting we have, we should never go over there. We should stay here. Here, only here, we get dyadic. Yeah, only here can we keep more physical meaning of the data rather than got to the constant amplitude. So the theory is true for all other high order spline. This is cubic. If you go to fourth order, it's the same. That means as long as the in between, you get that many points. And this theory actually covers the conjecture. So they come to the same conclusion. So therefore, the definition of IMF is an approximate definition. It's not the exact definition. Yeah. And to achieve that, we will never get exactly symmetry. We get approximate symmetry. And the approximate symmetry now was replaced by try to get the dyadic decomposition. And if we try to get dyadic decomposition, we try to stop it around 10. Yeah. So that's the moral of the theory. Okay. So that's we talk about one conjecture, one theory. Now we get the idea of how we should implement the EMD. How can we get to the? Oops. No wonder. Okay. We still have time. We should keep on going. Okay. Maybe I can even cover this. When we do EMD, we not only want to get the time frequency. There's another important information in the EMD, that is the trend. Trend is very important. If we have a data, if the data has a trend, can we do Fourier analysis? No. Yeah. Can we do mean? No. Because the trend is there, the mean doesn't mean anything. And if the trend is there, the Fourier analysis automatically repeat the data. So the trend itself will actually create a whole period wave, and the whole Fourier analysis is dominated by the trend. So to do a Fourier analysis, to do even statistics or whatever, none of that can tolerate trend. Yeah. But exactly how to take out the trend. The operation to take off the trend is called the detrend. Yeah. Trend is very useful information. Many of the experiments that we got, we don't get random data. When the final analyze, we want to get one variable versus another variable, and that variable has a relationship. That relationship is trend. It's not random. Yeah. So that's what we want. This trend, detrend, we specifically talk about this in a paper in the National Academy of Science, published in 2007. The motivation of this is from this work that is done by a colleague of mine at GADA. What they did was to measure the Greenland ice thickness and using satellite. Each time they analyze, they get the data like this. The data jump all over the place. And they want to know whether the global warming make the Greenland ice thicker or thinner. Okay, is it melt more or actually accumulated more? So they get the data. They want to find out the data. I want to tell you, the data looks like this cross, jump all over the place. Yeah, they want to find out the trend. If you go anywhere, even go the most sophisticated statistician, when they want to look for trend, what they do, they draw straight lines. This is the straight line that they draw. There's only one way to draw straight line, one fair way to draw straight line. It's the least square. That means this line will have to deviate from this to the smallest deviation. This is the fair trend. And this was actually first proposed by Gauss, least square distribution. So if we follow least square, there's only one straight line. Yeah. So everybody draw this one straight line. It becomes so boring. Yeah. The first one draw the straight line, and the second one has nothing to do. So the people tweak the data a little bit and get another straight line. So this is better. But all the lines are about the same. So then my colleague had a great idea, quote unquote, great idea. Said, no. So we should not draw a straight line. We should actually draw a line with this. What is this? This is seasonal curve. So in wintertime, it should be a little bit thicker. Summertime, it should be a little bit less, and high, and low, with the periodicity of 1 year. If we use the periodicity of 1 year to fit the curve, and then the curve will be a straight line plus a sine wave. The sine wave has different amplitude, but the period is the fixed 1 year. So then he claimed that his straight line is better than other people's straight line because he has this sinusoidal curve. Yeah, this is how this straight line fit the data. He called this trend. I cannot believe it. What if I have data like this? Then how you draw a line, straight line through it? These two data is totally different. This is from 1984 to 2000. This is from 1850 to 2000. This is the Nasdaq stock market price. This is global temperature. Yeah, and they all look the same growing up, but they are totally different things. That on different time scale, different amplitude. This is over 100 years. This is only 30 years. Yeah. So the stock market change has nothing to do with global warming and vice versa. Yeah. How to draw lines? We cannot draw lines. So nobody draw lines, draw straight line over this. Yeah, because because this is the stock market. This means the real money. And if you draw a straight line wrong, then you lost a lot of money. So that's a real thing. Yeah. But this, people still draw straight line. Yeah, and people draw straight lines. I will show you later how they draw straight lines on that. The data, oops. Yeah, this is the line. Here is the same data. This is how they draw the straight lines. The art to draw straight lines first. This is what I teach you. It's a great lesson to learn. Okay. If you have data look like this, you think they shouldn't draw straight line. But what if you make this axis longer? Yeah. So look flatter. The same data look flatter, then the straight line is almost possible. Yeah. This is the work that win Nobel Prize. Not in statistics, not in math. Peace. This is IPCC report. But we'll first talk about this. Okay. So to draw lines is a very important thing. People cannot handle data with trend. So what they do, they difference or differentiate. The data, any data has a slope. I take differentiation, I'll take the slope out. That's their idea. If your data is alpha times t, then take derivative, then of course becomes alpha, so the t disappears. But how do you know it's always alpha times t? Yeah, but to the first order, alpha t does it. The other way is to filter. Yeah, the filtering has a problem. If I have a signal like this, in Fourier analysis, this signal repeats itself at infinity. Yeah. So you do filter. You filter this, try to filter this out, and that filter has to contain lots of harmonics, because this is almost like a sawtooth information. So how many harmonics you got? Infinite. So by the time I took all the harmonics out, you take all the data out. Yeah. So filtering is no good. Regression. Again, how you regress, how you draw the lines through the data, that's another problem. We may have the time to do it. In EMD, however, the residual is the overall trend. The EMD residual is obtained not by filter. It's obtained by remove cycles. How you define cycle? Two extremas. I define cycle. So I took that out. So the trend is derived through remove all the oscillatory modes, not through averaging or regressing. Yeah. So that's the difference. So therefore, there's more than one trend other than the last one. You can stop anywhere as long as you tell people when you stop and what's the time scale. So this is the same data, the global warming data. This is how IPCC treated. IPCC said that, okay, I draw a straight line. Looks pretty good. Okay, I draw another straight line. Looks still pretty good to this data. I draw a third straight line. Looks good for that data. I draw a fourth straight line. Look this. So based on this, you see the first straight line, the slope is here. The second straight line slopes steeper. The third straight line is even more. The fourth straight line is the steepest. Based on this, IPCC claimed that because this line is steeper and steeper and steeper, especially when we get to close to the present time, it becomes the steepest. So the slope is the highest, the largest. Therefore, the global warming is accelerating from a very slow rate to a very high rate. Yeah, this is what they claim, and this is what made the newspaper, New York Times, whatever. Everybody carried this. This is based on the steepening of the slope of global warming is accelerating. Yeah. Before we get to the slope, we have to ask, say, if we look at this data, is this data, should we immediately process the data? The data, whatever they use, each of this is an annual average. Average over a whole year. Yeah. Average over a whole year get this point. And this is the range of that 12 month in there. So if you look at the original data looks like this. This is the original data. This is original monthly data. Each one represents 1 month, and this fluctuates up and down. Yeah. Now, on top of this data, this green data, this green means the coverage. Yeah. This is 1860. 1860, 150 years ago. Over the globe, how many places has a thermometer to measure the temperature of the global temperature? It's only 20% of the Earth is covered by the thermometer. I bet in 1860, probably the whole China has no thermometer. The thermometer was invented about 300 years ago. But by 150 years ago, very few thermometers around. You have to observe the temperature every day and record it. No chance. Yeah. So the coverage of the data is very low, and now 90% of the Earth is covered with data. So this green line means coverage. And this coverage has 2 dips. We dip here, we dip here. These 2 dips are also meaningful. The first dip is around 1915, 1920. That's when the First World War, and people were fighting, so nobody turned their thermometer. Then 1940 to 1945, the Second World War. When they fight war, nobody wants to take care of the thermometer. In fact, if you look at the temperature station in Taiwan, the Taiwan temperature station was established by when the Japanese come in 1895. Immediately after that, they established that. Okay, there is a big gap over there. It's 1945. When the war get into high gears, nobody look at that. So, what is annual average? I have give you monthly. So what is the annual average? Annual average is from January to December, add together. Average is annual average. And to think that annual average, think the different way. January, February, 12th. January, February, December. Okay, so annual average is list the data in this way. Yeah, then you average. So this is actually, then I can look at the data. I can look at data. I say, I want to look at the January data. The January data is 1 in 12 downsample. Right? I take 1 and skip 12, and skip 12. I get January. I take a February, again it's downsample. So if I downsample 12 times, I get 12 curves. Each one represents a month, right? So this is actually 12 to 1 downsample. There are 12 curves. One represents each month. The average of these 12 curves is the annual average, right? So the annual average is nothing but 12 to 1 downsample average. Yeah. Once you get January, February, March, and then you average this, you get it. You get it. Now, when you look at this, you immediately struck your eye. The data is very clean over here. It's very noisy here. That has reason. Why? Because the data is very good coverage, and very poor coverage. So the data are not very uniform. Some are very good. You look at this, the data looks good. Look at this, data is very poor. Yeah. So here you have very large variation. There's very little variation over there. So the annual average itself has slight problem. It's not an easy operation. Now, before we do that, we should say, what is a fair annual average? That is the first problem we have to attack. If you average this, you get that. And this is the standard deviation. The standard deviation is very large here, very small there. This black curve is exactly what they use. Yeah, 12 to 1 downsample average. So now, if I add up all January, if I add up all February, and I plot, I find that January, February, March, I find that monthly oscillation looks like this. Our monthly oscillation is much more than 0.1 degree. I have to warn you. What they have is already removed the annual cycle. The climatologist, in the climate, what is the largest change? Largest change is seasonal. Summer and winter, easily 20 degrees, right? In most of the places, 20 degrees. Even in Taiwan, it's 20 degrees. Taiwan's change is small. Summer times 30-some, winter times in the teens, so 20 degrees. If you go to higher latitude, the change can be 30, 40 degrees. So the annual cycle, the seasonal cycle is very large. How to get rid of that? The climatologists use 30 years mean. Yeah, I average 30 years, I get a cycle, and then take that away. So when you get this, it's called the global surface temperature anomaly. It's deviation from the mean. Yeah. Still, the deviation from the mean, you see the summertime is the warmest, the winter time is the coldest. But this curve is irregular. This curve is not smooth. That means the data has a problem. Yeah, March certainly is not the coldest. July may be the warmest. Yeah. Not only that, each of these January has a mean and a standard deviation, right? So I plot the standard deviation up. So the standard deviation, look at it. Wintertime standard deviation is very high. Summertime standard deviation is very low. Again, reasonable. But this curve is irregular. The curve is irregular. We certainly have lots of variation in winter times. The winter times, even in Taiwan, the winter times fluctuation is high. Like I have a cold front come, the temperature drops to the teens, and then the next day the sun comes out, it's raised to 20. Yeah, so 10-degree difference in winter time is nothing. But try to find the 10-degree variation in summertime. So I warm up to the 30s, suddenly drop to 20s. There's no chance that happening. Why? Because in the summertime, the air is very wet, and humidity contains a lot of heat, so it cannot lose that fast. So in summertime, the day and night temperature difference is also small. It never cools down. In the wintertime, the day can be very warm, the night can be very cold. So This is wintertime mode. This is summertime mode. Yeah. Qualitatively, they are all correct, but quantitatively, I have problem with that. This is so unsmooth. Yeah. So now, I think I'll keep this in suspension. We will come back to discuss how can we make it clean. Yeah. And you can also go back and think, how can we make it clean? Should we use filter? Should we use whatever way to make the annual cycle looks right? Okay, and make the data looks clean, and make this kind of average looks reasonable, and what is the correct answer. So I'll stop here, and then we'll continue next time to talk about the trend, and then we'll talk about the multivariate and multidimensional EMD. Okay, I'll stop here. Any questions? Hi, any questions? No question, huh? No questions? You have to beware. I'm coming to Tokyo. I'm going to ask you questions if you don't ask me.
Okay.
All right. Sayonara. See you next time. All right. Bye-bye. Turn off. You have any questions? 有没有问题啊？没有问题，我们就下课了啊。我再问一次，没有问题 ，OK， 下课。